Let's do it. Okay, welcome to this materials physics seminar, and we have a special guest today, Professor Gerald Seidler from the University of Washington in Seattle. He was actually a PhD thesis opponent yesterday and did a great job as an opponent. And he is specialized, and his research group is renowned for significant improvements and the development of different kind of X-ray spectroscopic methods based on synchrotron and home laboratory, local laboratory settings. He is a co-founder of a company that is very well known around the world now. It's called XAFS, and this talk will explain what is XAFS. He has been working with many different kinds of materials, battery materials, electrodes, electrolytes, photovoltaics, and now also materials related to the long-term storage of spent nuclear fuel. And this is very much related to what we do here on the campus. I'm really happy to have Gerald here today, and please go ahead.
Thank you. Is that the microphone on now? Great. Today we're going to discuss the history and future of X-ray absorption spectroscopy. And the motivation for why I prepared this talk was it being roughly the 50th anniversary of this paper. So this is a paper by Sayer, Stern, and Lytle. Ed Stern was my a former late senior colleague at University of Washington. And it's really a fascinating paper. You can see that it's called A New Technique for Investigating Non-Crystalline Structures, Fourier Analysis of the Extended X-ray Absorption Fine Structure. And what this paper did is really kind of fascinating. I'm sorry, I have something on the screen I need to get rid of. There we are. It fixed an idea at its heart. And what it said is a core level photoelectron is very different than a hot electron in a high energy band. It also gave a correct theory for X-ray absorption spectra prediction. So already that's a pretty impressive paper. But even further, they realized that they could give at least a first step method for X-ray absorption spectra interpretation. And I'm going to develop the history to explain why this is such a remarkable paper. But a lot of the proof for why a paper is important is that people actually celebrate the 50th anniversary of it. And so, in fact, yes, there already was a symposium at Brookhaven National Labs for the 50th anniversary of this theory of extended XAFS. There was going to be special sessions on the 50th anniversary at the conference that would have been this summer in Chicago, but has been, am I echoing? Okay, but has been delayed till next year. And another reason that you can tell this paper is likely important and is still in use is other international societies such as the IUCR care about XAFS, and they care about quality control in XAFS interpretation. So how else might we imagine that this technique is important and this paper is important? So this is a map of the world, and each one of the little symbols is, most of them are synchrotron X-ray sources. A few are free electron lasers, not worry about it. The difference in color has to do with whether they've paid the website or not to be a member. It doesn't have to do with whether it's turned on or not. I'm pretty sure that's right. And there's about 40 synchrotrons around the world. And this would be a typical one. This is the advanced photon source located outside Chicago. And what's shown here is a sector map. And so at each of these sectors, you have 1 to 4 X-ray beams coming off, and they can all be used simultaneously. So there could be as many as, perhaps 100 or 110 experiments all going on simultaneously. Each of the sector labels that has the yellow highlighted box around it does XAFS or something closely related. So that's a pretty significant fraction. At most synchrotrons, between 10 and 20%, but sometimes as many as half of the sectors are doing XAFS or something closely related. Well, I said there's 40 of these around the world. They're kind of expensive to build. They're expensive to operate. And so if you add up the total expense, sort of take the fractional expense of building the synchrotron, plus the cost of building the sector, plus the cost of staffing the sectors, you get an estimate of about $7 billion US spent by governments around the world to make XAFS available to researchers. Of course, the synchrotrons are overwhelmingly user facilities, where there's a proposal process that the reviewing team tries to choose the most promising, most cutting-edge science to give access. And that's resulted in somewhere between 50 and 100,000 publications using this technique. But typically, there's an unmet demand that's anywhere between 3 times and 10 times between where you are in the world. There's limited industrial access, and there's certainly no analytical or process access. So XAFS as a technique is not a part of routine analytical chemistry, at least at synchrotrons. So this raises some questions. What's the science? I mean, $7 billion, that's more than the Large Hadron Collider cost to build. So there better be some pretty impressive science coming out of these 100,000 papers. And again, this largely came from fixing an idea about photoelectrons. And then what can be done about the unmet demand? So that was for a sort of a pre-introduction. As you'll see, I'm going to talk about the history of X-rays leading up to XAFS and beyond. And as Simo said, I'm at the University of Washington, and at various points in our efforts to get XAFS working for more people in more places, I've been fortunate to have a wide variety of funding. So I'll review for the audience, even though I know many of you are in the X-ray group. X-ray absorption, we can imagine as being a photon comes in and perhaps it excites a 1s electron, and then you have to have some unoccupied density of states above the Fermi level for the electron to go to. X-ray fluorescence, of course, is the decay process, and that can be radiative or non-radiative. When it's radiative, it's X-ray fluorescence. So this is a coarse plot of the absorption coefficient of cobalt as a function of incident photon energy. And there's 2 important things here. One is that your intuition should be, and it's seen here, that the absorption goes down as the photon energy goes up, right? Optical light, UV light doesn't penetrate through our bodies, gamma rays do. Higher energy photons penetrate better. The other thing you'll see here that you should have expected is every time you hit the binding energy of an atomic shell, well, now there's another way for photons to be absorbed, and so the absorption coefficient goes up. If we look closely at the cobalt 1s binding energy, we then see wiggles, and wiggles is not a good enough academic term. It doesn't sound professional enough, so it's fine structure. But in spectroscopy, we're always talking about wiggles. And so this is the X-ray absorption fine structure. Here the material is the battery material, lithium cobalt oxide. The first 30 volts or so after the binding energy are called the X-ray absorption nearite structure. And then after that, the extended XAFS, the extended X-ray absorption fine structure. The distinction here has to do with damping mechanisms, and you end up needing different theory to treat the region near the edge and the region away from the edge. The region near the edge is commonly used for looking at oxidation state, crystal field effects, coordination, geometry, and so on. And the extended oscillations give you bond distances, coordination numbers, and immediate local structure. This is the outline of my talk. It's graphical, which I think ends up being useful in a historical talk. And so we're going to start in 1895 with the discovery of X-rays. After that, there's about 25 years where the scientific community simply wanted to know what are X-rays. Okay. Once it was understood what X-rays are, near the end of that era, X-ray absorption edges were observed for the first time. And that was interesting. But then fine structure was discovered. And you'll see it took a long time until we got to this work of Sayers, Stern, and Lytle before there was a strong theoretical interpretation. There then was an era of development of XAFS expertise and fundamental knowledge of how to predict and interpret this. There then was an extensive era when XAFS was only done at synchrotrons. And now we're in the last era, I would propose, where XAFS is evolving out of being an expert technique that's narrowly used and becoming a routine analytical technique with much broader population. So let's work through this timeline, starting with Roentgen. So Roentgen was in his lab on 8th of November, 1895, and he had a cathode ray tube, and he was investigating cathode rays. And he had an experiment where we would now say the electron beam, though electron wasn't even discovered at this point, is being accelerated toward an anode that has a complex shape like a cross. And some of the electrons will overshoot. And if you put a fluorescent screen here, you'll see the shadow of the shape of the anode. And this was the experiment Roentgen was doing. And you can see you have the barium potassium cyanide fluorescing screen here. And he had some spare fluorescent screen outside the vacuum tube. And he saw it glow. And you just kind of want to imagine what he was thinking when he saw that. If it was me, I would have immediately turned the high voltage on and off a few times and seen it blink. And then I would have found someone else to come and look at it. It would have been an amazing day. His diary certainly speaks of him being amazed. And he didn't know what this ray was. He knew it couldn't be cathode ray because cathode rays wouldn't penetrate the glass and don't go through air. And he said, okay, the symbol for the mathematical unknown is X. I'm going to call this an X-ray. And someone else will have to figure out what X equals. So he did so. Of course, almost immediately, the potential medical applications of X-rays were known. And this was a profound and important discovery. And he received the Nobel Prize in Physics in 1901. So X-rays are absorbed differently by different materials. That's good. And right away, right, what is X? And so one of the earliest proposal is this is a very high frequency electromagnetic wave. And the very first experiment failed, right? The very first experiment would say, all right, it's an electromagnetic wave. We know that they refract. So let's look for refraction of X-rays. And it wasn't possible to observe with the beam quality at that time. And there wasn't an understanding of how small the deviation from unity of the index of refraction would be. So the question kind of continued, what is X? Until von Laue. So if you read Max von Laue's Nobel lecture, what comes across is an enormous humility, is a discussion of how he was going to the lab one day and wondering about X-rays and thinking, well, I don't know what the wavelength of X-rays are, but I know roughly what the spacing between atoms is in a crystal. Maybe it's about that size. And he did the experiment, and he put up a piece of film, and it probably ran overnight, and he came in the morning and must have had a very good morning. And he saw the spots, and as soon as you see those spots, it's game over, right? This is an electromagnetic wave with wavelengths about the size of the spacing between atoms and crystals. The Braggs, of course, also studied diffraction and made it very quantitative. And there's a considerable discussion of the history of determining that X-rays are part of the electromagnetic spectrum by Compton in his Nobel address. And it's a very enjoyable read if you like X-rays or science. All right, so the Braggs, of course, came up with the equation n lambda is 2d sine theta, where theta is the angle of grazing incidence. And for today, it's going to be useful to recast this as the energy diffracted as a function of Bragg angle is the energy at backscatter divided by the sine of the incident angle. And so key point here is a known lattice spacing allows determination of an unknown photon energy, right? As far as the Braggs are concerned, the purpose of diffraction is to determine a crystal structure. But once you know a crystal structure, you can then use that crystal as a dispersing element in a spectrometer. Speaking of spectrometers, Mani Sigban is well known for many discoveries and also for the very detailed experimental work for the development of the first really high-resolution X-ray spectrometers, and also received the Nobel Prize for his work on fluorescence from atoms. And let's just take a minute to understand the simple spectrometer, the rotating crystal spectrometer. So suppose I have a collimated X-ray source that's polychromatic, and I have my diffracting crystal here. And perhaps for the lowest energy X-rays, the longest wavelength X-rays, this is the geometry when you would scatter off of those crystal planes. And then you go to a little bit higher energy photons, a little bit lower Bragg angle, and now you get the green and then the blue. So highest energy will be closest to forward scatter, lowest energy will be closest to back scatter. And in the old days, this was recorded on a photographic emulsion. And so you would bring in your beam, maybe it was you were studying the fluorescence of titanium, and so you had titanium as the target inside an X-ray tube. And you would rotate the crystal to expose all of the film and then develop the film and see your fluorescence lines. So this turns out to be, I mean, an incredibly big deal scientifically, not just because it's nice to know binding energies in atoms and fluorescence lines in a Bohr model, for example, but because there was a very difficult problem in the world, and that is, what is the periodic table? And so Mendeleev proposed the idea of a periodic table in 1871, and there were many competing periodic tables. The most beautiful one here is by Crookes, the same Crookes who made the X-ray tube, the Crookes tube. And you can see it's a sculpture. It's a double helix, or I don't know if I should call it a single helix. It's a two side-by-side helix periodic table. And you can see there are some mistakes. Here in group 16, you're missing oxygen, which somehow has appeared over here in group 7. Some of the transition metals aren't distinguished. And so it really was uncertain what the periodic table looked like because no one had measured atomic number, right? The Bohr model was out there, but no one had measured atomic number. So then along comes Henry Moseley. And this is a famous figure called Moseley's ladder. And so this is successive data taken for different elements in an X-ray tube. And you can see increasing photon energy is to the left. And so here is the spectrum observed for calcium. Excuse me. Observed for calcium. The lower energy line is K alpha, which is 2p to 1s. The higher energy is K beta, 3p to 1s. And now we have titanium, K alpha, and K beta. And you can see we've got this ladder where as we move from one element to the next, the binding energies increase, the differences in binding energies increase. And so you keep moving to a progressively higher Bragg angle in that sig bond spectrometer. And then you can glue everything together and come up with these spectra. Here you can see there's some nickel impurity in the cobalt. Here's brass, which is copper and zinc. And it all works. And what he noticed is that the energy of K alpha, the square root of the energy of K alpha, goes as an integer. And that integer in the Bohr model turns out to be the atomic number, the number of positive charges in the nucleus. So this fixes the periodic table and in fact found 4 gaps. Technetium, and I've forgotten the other 3. And a few of them, I wish I could remember which 4. A few of them were just extremely rare, and a few of them turned out to be radioactive and very difficult to find. So this solved the periodic table. It was the first great application of X-ray spectroscopy. And this is, sorry, all the X-ray aficionados in the audience are going to run out to eBay and buy this. It's about $12. This is the commemorative stamp from Maurice de Broglie. So Maurice de Broglie is credited with extensive work on X-ray fluorescence, including the first strong evidence for an absorption edge at X-ray energies. And I'll show you that in just a minute. But first, we have to talk about this stamp because people in this room build spectrometers. So I feel safe to say that this is the single greatest postage stamp with an X-ray spectrometer ever. It may also be the only stamp, but that shouldn't be taken as a negative perspective because it's wonderful. And so as you move from left to right, you can see the high voltage generator, the scale-up coils here, the transformer coils. Here's the X-ray tube with the electron beam hitting a target and fluorescing. Here's entrance slits to make a collimated beam. Here's the rotating crystal, and then the film screen. So in my opinion, the perfect postage stamp, and still available online for those who are interested. So let's look at this early data. I've actually found it very hard to find de Broglie's original picture, but about the same time, Ernst Wagner, who had been a PhD student of Roentgen, did a very similar experiment. And so here, he's using the rotating crystal spectrometer to look at the Bremsstrahlung from an X-ray tube. And he's using a silver bromide emulsion. And whenever energy is deposited in the film, it turns black. So here again, increasing energy is from left to right. The top and bottom are seeing exactly the same radiation, but there's an added neutral absorber here to prevent saturation of the film. And so as you move from left to right, you see some fluorescence lines, and then a sudden step where things get dark, and then another sudden step where things get dark again. And if we play with the math a little bit, we can find that the first step corresponds to the bromine K edge, the 1s binding energy of 13.5 kilovolts. So when you get there, the X-rays don't penetrate through the film. Instead, the X-rays are more preferentially absorbed by the film, and the film blackens. And then the same thing happens at the second step for the silver K edge. So this is how the existence of absorption edges was first discovered. A few years later, Hugo Fricke, who was closely related with Bohr and Lyman and Sigbon, was measuring transmission through V2O5, and he saw fine structure. He saw wiggles, and he was convinced they were true, even though you might say they're kind of at the limit of the systematic error. And you can see here what the correspondence is with modern data, and it's not bad. Right, both of these minima are real. This small maximum is real. This pre-edge feature is real. And so there's more to X-ray absorption than just the photoelectric principle that when you hit a binding energy, there's more absorption. Something else is going on. It was quickly realized that the fine structure had something to do with crystal structure, and the success of X-ray diffraction and the emergence of quantum theory made XAFS a very hot research topic for decades after that. And from a practical perspective, what happened is scientists stopped building spectrometers to study fluorescence and what are X-rays, and they started building spectrometers to understand what is the X-ray absorption fine structure. So there's a sequence of beautiful experiments by Donald Hannevalt, who is absolutely famous in the powder X-ray diffraction community as the father of analytical powder XRD. There's international awards named after him. But in his younger days, he studied XAFS, and he did these three lovely experiments. So first, he did an experiment here. Again, what we're seeing here is the transmission through some samples. Here, the sample is zinc solid. So when you hit the absorption edge, the absorption coefficient goes up, which means the transmission goes down, and then you see fine structure. And then he had a furnace where he heated up the zinc enough to get enough vapor in the beam path to do XAFS on zinc vapor. And now there's no fine structure. So a solid show fine structure, isolated atoms do not. He then did another experiment, this time on the very toxic material arsenic trichloride. And he compared transmission through the solid phase with transmission through the molecular vapor. And one hopes that his safety people were aware he was doing this, but I don't know if there were safety people in 1931. And what you can see is in both cases, there's fine structure. Again, this is the transmitted signal. So the absorption edge means the transmission goes down. There's fine structure in both cases, but it's different. And so that means you're not, right, this is a molecular solid. And so that means the XAFS is not just sensitive to immediate chemical bonds. It has to be sensitive to something in the first shell and beyond the first shell. This is wonderful qualitative work. And then the last thing he did is he said, okay, X-ray diffraction. We know that as temperature goes up, the atoms shake more and that affects diffraction. What about this fine structure? And so the energy scale is reversed here. I apologize. Here's low energy going to high energy. There's the strong absorption. So the transmission goes down. And you can see many oscillations in, this is the spectrum of metallic iron. And then at 840 centigrade, the oscillations are strongly damped. So something that matters here is the distance between atoms and, let's say, the distribution function of distances between atoms. So we're getting a lot of information in a very qualitative way from this sequence of experiments by Hanneveld. So as of 1931, there was a set of experimental facts. Atoms have no extended XAFS. It's a consequence of the environment. Molecules have XAFS that's distinct from the molecular crystal. Similar crystal structures have similar XAFS, but the features move in energy inversely with lattice constant. So the smaller the lattice constant, the wider the features become. And high temperatures quenches the oscillations. As far as the near edge structure, they saw that every crystal structure had a different near edge structure with no particular commonality at the time that they could interpret. And it was known that the binding energy shifted with oxidation state usually. Okay, well, that's a lot of facts. And at some point, you need some theory. So Kronig gave a very influential approach to this. And Kronig, of course, is very famous for a number of theoretical developments during his career. And he ended up with two theories. For crystalline solids, a band structure, of course, had only recently been discovered and developed. And he stuck with the ideas of band structure and said the oscillations are due to looking at the alternating band gaps at Broughon zone boundaries. And he had an idea how that could be, each peak could correspond somehow to when the energy of the photoelectron and its momentum were coincident at Broughon zone boundaries. And then for molecules, he said, well, we need a scattering model where we have a photoelectron wave going out and you have to worry about the constructive and destructive interference and so on. There was some belief, there was qualitative agreement with many experiments. Certainly, as soon as you bring in the band structure, you're going to correctly get that the features become more widely spaced as the lattice constant goes down. This is before electronic computers, so there was one mechanical computer built to calculate scattering for XAFS in a molecule, and it looked okay. A scattering calculation looked good, but there was no other quantitative test of the theory for decades. A problem came up shortly after, though it wasn't recognized for some years how important this was. A problem came up a few years after Kronig proposed his model. So this is a modern interpretation of the argument from Takeshi Hayashi. And again, here, energy is going backwards from right to left. So increasing energy above the edge is toward the left. Absorption is going down. So this is a good, fairly modern-looking XAFS transmission signal for nickel. And the dilemma is that if you take the Broughon zone boundary model of Kronig, this is what you expect. And so maybe you can find some places where peaks match peaks, but there's certainly too much structure predicted in the Kronig theory. On the other hand, Professor Hayashi said, well, what if I just ask, when is the de Broglie wavelength of the photoelectron comparable to the spacing between crystal planes? And that looked pretty good, right? Not perfect, but here's a local maximum. That's the 224 separation. Here's a local maximum. There's the 400 separation and so on. And so he proposed the idea that there's sort of quasi-stationary states, electron standing waves, if you like, that are available as final states for photoelectrons. And when that occurs, the absorption is stronger. It's a good idea. Again, the Kronig theory was quantitatively weak and also predicted polarization effects that don't exist. There was a number of scattering-based ideas that were proposed several times, including this one we're talking about, before 1971. Some other ideas also came before Sayre, Stern, and Lytle. So Yvette Cauchois, a famous X-ray spectroscopist from France, and Sir Neville Mott, who later received the Nobel Prize for metal insulator transition, worked together to try to understand why in some cases you get a strong enhancement of absorption near the Fermi energy. And they ended up arguing, and this is very important, they ended up arguing that there was an excitonic contribution to such peaks at the Fermi level. And what that means is that there's quantum states near the Fermi level that only exist in the presence of the core hole. And that those states are the ones that help contribute to the extra unoccupied density of states near the Fermi energy that gives this big feature usually called a white line. This is terrifically important because it says that the core hole is non-trivially breaking long-range order. It says that XAFS is not a ground state spectroscopy, it's an excited state spectroscopy, where in order to ask what are my final states available, I have to be solving a problem with a core hole at one site. So very conceptually important. Now we get to 1971 in the Sayre, Stern, and Lytle paper and approach. Lytle claimed that about 2% of all papers in the physical review before 1970 were on X-ray absorption in some flavor or another. What they proposed was a pure scattering model where there could be an atomic behavior that's modulated by interference from photoelectron scattering. So very similar qualitatively to the work of Hayashi from 1936. And they worked out the details of the scattering physics, including really all the details of the boundary conditions, including the fact that atoms are not hard spheres electrically, but you're going to get phase shifts when an electron scatters off an atom. And they came up with this expression. I've simplified slightly. The experts will please let that go, which is a path expansion where your path R is the distance the electron goes out and comes back when it's scattering. Again here, built right into this is this idea that as bond lengths go down, the oscillations are going to get more widely spaced. There's a lot of other stuff here. There's the disorder effect. There's a damping effect so you can build into mean-free paths. The scattering phase shifts and the scattering amplitude is very important here, right? As energy goes up, atoms scatter less and less well, very similar to a usual atomic form factor. And so that has to be properly accounted for. And then there's also multi-body corrections, which came along later. So this is a scattering formalism for either molecules or crystals. This is agnostic. It doesn't care what material you're looking at. The phase shifts have to be included. And if you know the scattering amplitudes and phase shifts and you know your structure, you can predict the wiggles. And the neat thing is, if you have no knowledge of the parameters, well, this is just a sum of sine waves. So you can Fourier transform and get out some kind of a distribution function in R in path lengths. So let's look at the first data from that paper. Up top is the Kaya V, again, the interference piece, the wiggles for crystalline germanium. And down at the bottom is for amorphous germanium. And I'll remind you that germanium is tetrahedrally coordinated, it's diamond structure. And if it's amorphous, then it's corner-sharing tetrahedra with relatively random rotations between the corner-sharing tetrahedra. So there's only one characteristic length in the system, and that's from the center of the tetrahedra to a corner. And if you look at the data on the bottom, it looks like there's one characteristic something about the oscillations. Up here, however, right, you also get finer wiggles with a finer period in photoelectron energy, really in wave number. And that's okay because there's more longer characteristic lengths in a crystal. Second nearest neighbor distance, third nearest neighbor distance, and so on. And longer distances means the wiggles have to get closer together. So this was the data. I'll remind you the fast Fourier transform was discovered in 1965. And so here in 1971, this is just showing the peaks really line up, right? The maxima line up, the minima line up. And so you would look at this and say, okay, I think the first shell is probably the same in both. And then you can go and do the Fourier transform. And yeah, in the glass, you only see one characteristic length. The peak is closely related to the bond length, but needs to be corrected for phase shifts on scattering. And then you can see evidence for a second and third and maybe a fourth shell in the XAFS for the crystalline material. So all of a sudden, you start asking, is this a diagnostic method? Because you take data, you Fourier transform it, and you're getting out something that looks kind of like bond lengths, even if the material's disordered, and that's something diffraction can't do. And also, this is element selective. So a lot of differences with respect to diffraction. John Rare came to University of Washington in the 1980s. Ed Stern convinced him, hey, why don't you work on theory for XAFS? It shouldn't be so hard. And so then John and his group spent 40 years completely solving extended XAFS. And again, this is the XAFS equation. And their theory work, it's called the PHEF project, now predicts every parameter in this model. So for extended XAFS, not for Zane's, but for extended XAFS, the problem is solved. All right, so where are we here? And I've got about 10 minutes left. I'll try to make sure I stay in the time window. So this paper fixed an idea, gave a correct theory for prediction, gave a correct method for interpretation. Why $7 billion? And the answers are many, spanning a huge range of fields in material science, environmental chemistry, fundamental chemistry, nuclear materials, batteries, space science, everything. And again, 100,000 papers at the synchrotron. But as it turns out, you can sometimes do XAFS without a synchrotron. And that's what I want to spend the last part of my talk on. So let's look at three cases: interstellar dust, battery chemistry, and catalysis. All right, so for XAFS, you need an X-ray source. And if synchrotron time isn't available, then oh, sorry. So I just want to point this out. If you're not using a synchrotron for XAFS, that's very strange to the people in the community. So Farrell Lytle, one of the XAFS discoverers, had a reminiscence paper in '99 where Farrell had built for many years XAFS spectrometers at the Boeing Corporation. They had a basic research lab. And he says once the synchrotron started, that was it. In one trip to the synchrotron, we collected more and better data than in 10 years in the lab. He went back to Seattle and turned off all his spectrometers and never turned them on again. Okay. So by the early 1990s, no one trusted laboratory XAFS anymore, and it largely died, not completely, but largely died out. So if you don't have a synchrotron, the obvious thing to do is to find an X-ray binary and use that to light your sample from behind. Okay, maybe it's not the obvious thing to do, but you could do it. And so this was done in a space experiment with the goal of understanding what's the local structure in interstellar dust, to try to determine what is the mineral phase of silicates in interstellar dust. And so this is a transmission mode measurement. I have an X-ray source that's 15,000 light years away from Earth. It's relatively spectrally flat, below about 3 kilovolts. And you're going to transmit through dust, and then you have a detector, which is one of these satellites. And this one is past commissioning now and is going to be amazing when they turn to this question of interstellar dust. But this earlier work from the Chandra X-ray telescope is already pretty neat. So photon energy is moving to the left. You can see the silicon K edge. You can see a couple oscillations, and the oscillations match olivine, which is a very common mineral on Earth. And so you've got some initial evidence that a fair amount of interstellar dust is a crystal phase that we know on Earth. It's pretty cool. All right, you can't go very far with the X-rays from space. So you have to get to an X-ray tube. And so again, the 1980s lab XAFS was largely rejected, and it was for 4 reasons. The detectors weren't good enough. They couldn't reject backgrounds that caused systematic errors. The optics often weren't very good, which gave you bad energy resolution. It wasn't that hard to get synchrotron access if you were an expert, and only experts were doing XAFS in the 1980s. And the automation really wasn't easy to do back then. So come 2013, when my group started looking at this, well, the detectors are insanely better, such as silicon drift detectors that are, for example, made in this building. The optic quality is shocking now. I mean, we're in an age of precision ground lenses that you can glue crystals onto and make any curved optic you want. Synchrotron access is now ridiculously oversubscribed, despite there being 40 synchrotrons around the world. And automation, every high school student does Arduino and does automation. Automation's no problem anymore. So in 2013, we had the idea that maybe we could quickly and inexpensively make a lab XAFS system. And the first thing that all of the old XAFS experts will recognize in this picture is that, why is this guy smiling? XAFS is usually a technique where you go to the synchrotron and don't sleep and no one smiles. But here's a guy doing XAFS and smiling. Something's wrong here. So that's Devin Mortensen, my graduate student, who subsequently became the chief executive officer of XAFS. And this was our first radiation enclosure, a wooden box called the coffin with lead stapled on the inside, a garbage bag full of helium for the helium space. And the spectrometer itself was similarly simple. An inexpensive 10-watt X-ray source that's often used in veterinary science to X-ray sheep. A borrowed spherically curved optic, and a inexpensive silicon drift detector on a couple of translation stages and another translation stage under here for the Rowland circle. From the idea to do it until the first spectrum was 37 days. And the first spectrum wasn't bad. And a month later, it was dialed in and we were nailing synchrotron data. Now, we were at 3,000 photons per second incident flux, where the synchrotron is at a few times 10 to the 12. But it turns out in transmission mode for concentrated samples, a few thousand is okay. So we pushed this for many years. We spun out the company, and come 2018 and a little bit earlier, the half-meter optics were available. And this design of spectrometer in the commercial systems is in about 120 laboratories around the world, and in homemade systems in another probably at least 10 labs around the world using very similar linear spectrometers, including some beautiful implementations here in Helsinki. So I'm going to show you some results now, and I specifically chose not to show results from my lab because the whole point is that everyone should be doing XAFS, not just old people like me who've been doing XAFS since back when it was hard. So this is a paper from a wonderful research program at Helmholtz Institute in Ulm. And what they're looking at here is battery cathode materials that are multi-element, that are high entropy materials, which ends up being very interesting in a wide range of material science right now. And it might be a little hard to see, but there's two metal sites. One is iron and one is mixed. And the cyanide atom, a cyanide molecule here, has a different length from the iron site as from the other site. And without going into the details, the extended XAFS taken at every element agreed that they really were getting this high entropy alloy that was doped only on the manganese site, if you like, not the iron site. And then they did the Zanes that validated the oxidation state and did some X-ray emission spectroscopy for spin state. So this is a comprehensive spectroscopic study for material science done without going to the synchrotron. This is a beautiful paper. This paper is from Lewis Piper's group at Warwick. And what they have is a pilot manufacturing facility for pouch cells. And so they did an operando XAFS study at the same time as an operando X-ray diffraction study. And by combining the two of them, they got insight into why the batteries were failing, into the battery fatigue. So purely analytical, and they could do it every day as they changed the battery chemistry. And so you look at this and start asking, could XAFS be part of quality control in battery manufacture? As a final example, we'll talk about catalysis. And so, as Simo mentioned, yesterday I had the pleasure to serve as the opponent in Antti-Jussi Kaleo's public examination. And among the work that he did is this paper in Angewandte Chemie, operando laboratory XAFS with multiple edges for solid catalysts. And this is beautiful data in quality and in the science, whereas the ratio of the three elements in the catalyst are changed, they're able to observe whether reduction is occurring or not on the three different elements, and thus whether there actually is a synergistic effect from using multiple elements in the nanocatalyst at the same time or not. So with that, I'll conclude. And we've gone through this history, starting with Roentgen, experts studying what are X-rays, experts discovering XAFS, experts arguing what is XAFS, experts developing XAFS, synchrotrons being built, and then around 2000, people who are doing XAFS at synchrotrons stopped being just experts. And then in 2013 and beyond, everyone can do XAFS, even not at a synchrotron. So it'll be very interesting to see where this goes in the future. As a last note, I'll remind everyone that there's a online seminar series that I helped to run. It's been going on since COVID. There's about 130 lectures on XAFS available at this YouTube channel, and some more will be added later this year. Thank you for your time.
Thank you, Jerry, for the beautiful talk. Beautiful, excellent, and very informative from the early days to today. We are a little bit short of time, but I would like to give the opportunity to ask questions or give comments from the audience here or online.
If no one is asking questions, I can ask one just because of my ignorance or something like that. So when you're talking about the fluorescence, do you have any idea about the quantum yield of fluorescence? So how much of the energy is coming back as light? And you talked about non-radiative transitions.
Yeah.
So what are the mechanisms of these non-radiative
transitions?
Well,
the non-radiative transitions will be Auger processes, which is where the energy entirely comes out in electron cascades. And yeah, the branching ratio itself was a topic of extensive study and calculation for a long time. As a rough rule of thumb for the 3D transition metals, the K-shell fluorescence yield is about 1/3, and it becomes less as Z goes down and becomes much larger as Z goes up. It's above 50%, but I don't remember exactly where for uranium K-shell, for example.
Thank you. Other questions, comments?
Yeah, great talk. So this was very nice overview and kind of a full circle that how, you know, it comes back to this in-house technique development. So what are the next, let's say you already kind of kept it open in the end. So what are the major bottlenecks in making it like, you know, even more usable in-house? Is it like samples, or is it you know, more?
I think there's many answers to your question. You can approach it from the standpoint of how to find, for example, one way to start is to ask how to find more users. So the technique is certainly underutilized. That's become clear. So it is not the case now that everyone who gets a bachelor's degree in chemistry would know what XAFS is and what it might be used for. And in the past, it made sense that that was not part of the standard curriculum because not every undergraduate gets to go to the synchrotron. So one important thing would be to include XAFS in teaching, which in some cases could be done with the home-built or commercial machines, but those are rather expensive, and something we've worked on and off is coming up with an inexpensive one-element spectrometer for instructional purposes. So I would say instruction is one forefront. A possible outcome partly with instruction, partly with instrument development, is the use of XAFS in quality assurance in industrial manufacturing. And then in between there is just expanding the scientific reach. From a technological perspective, more flux is always nice. Better optics is always nice. Operando cells are outstanding. But to me, the really interesting stuff is on those two endpoints, which is instruction, so the technique can be used by everyone who actually does need it, that they'll know it exists, and then possible industrial use in very analytical ways.
Thank you very much. I think in view of time, we will close the official session now, and but Jerry will stay here for a little while,
Of course.
before you have to go to the airport.
Yeah.
But please stay for questions later on. So I'll just close the recording, and thank you very much. Let's thank
Thank you
Jerry
again.
again.